All right, so we agree that this should really say 5,760. But the main thing is this amount of carbon 14 to carbon 12. The ratio is more or less constant. And so when you dig something up, that has died. It could be a plant, it could be animal, and as long as you're within 10. So let's say 10 times this is less than 57,000 years, right? Or more, actually a little bit more. But um, so you would never use carbon 14 for anything. In fact, you'd probably want to stay away from the 10 10 half lives, but it would have to be less than 57,000 years, right? So I'm just adding another zero to this, so for 10 half lives, um, because at that point there's so little carbon 14, you can't distinguish it between that and the background. All right, so non-living things, dated through uranium, um, and lead isotopes. Okay, so this is the thing about the carbon 14. You always look at the ratio of carbon 14 to carbon 12. With when you use uranium, so this is the most abundant. You find uranium on the Earth. It's more than likely it's going to be. There's only a small percentage of it that's uranium 235. So the most common type of uranium is uranium 238. It has multiple daughter atoms, but eventually it becomes this this rather rare isotope of lead, but it's stable. It's a very stable isotope of lead called lead 206. So if you find something that is under, that had uranium in it, let's say the Earth, for example, right? And this is how we know the age of the Earth. The uranium 238 has a half life of 4.5 billion years. Um, so when we dig into the Earth, we find um, you. Oh, actually, remember, you're just doing this with non-living things, right? They're not living things are very unlikely to have any kind of uranium in them. Um, so for we're talking about like rocks and things like that. Now you don't really find rocks that are as old as the Earth itself, like laying about. That's actually somewhat rare. But there are rocks that fall to us from the solar system, right? That those are meteors, right? There's meteors that fall that we have access to, and then there's of course we have gone to asteroids and stuff like that. And so we've done this with our moon too. We've gone there, and so you take you measure the amount of uranium 238 that's there, and you measure the amount of lead 206 that's there, and every single. So this is what I want everybody to understand. This is really important. Every single time, you always find that whatever has the uranium 238, there's always lead 206, but there's an equal amount of uranium 238 and lead 206. In other words, one half life has gone by, right, since the beginning of the solar system. So this happens with asteroids that we found, with meteors that we found, with some really old rocks that we found. You can't get all the way to the 4.5 because the Earth is recycling itself, and so the rocks are never exactly 4.5 billion years old. So 4.5 billion years, that's the half life of uranium 235. And you can do a similar study with uranium 230. I'm sorry, with uranium 238. You can do a similar study with uranium 235, which becomes another type of lead 207. Now this has a different half life, but you can it's these things help. These are really long half lives. There's other types of um, isotopes that have really really long half lives. I think one of them is like potassium 40 or something like that. So an archaeologist uncovers an ancient spear whose wooden handle contains 1/8. Okay, so right away, as soon as I see 1/8, I know that 3 half-lives have gone by for the carbon-14, right? So three half-lives. So it's going to be greater than 1,000. It's greater than 11,000 years, right? Remember, one half-life it would be 5,700 years. Two half-lives, 11,000, and then so the answer should be this one. So it's going to be 3 times the half-life, right? Because 1/2 raised to the third power is 8, right? All right, so so 3 half-lives have gone by, and remember, you can find it doesn't have to be exactly this. This works in between as well, right? In between 11,000 years and 17,000 years, you can figure out how old something is. All right. It doesn't always have to add up to exact. It doesn't have to be exact numbers of half-lives that go by. All right. So now we turn to what's called nuclear fission. Okay. So fission this was the first thing that was that was discovered. We, of course, used this phenomenon in World War II. Right at the end of World War II, there was a secret project that was going on. It was called the Manhattan Project in the deserts of New Mexico. In the desert of New Mexico, and so here's basically what we discovered, and this was discovered beforehand. In fact, the very first time that there was fission of uranium-235 was, I think it was at the University of Chicago, and it was done by a guy named Enrico Fermi. You might have heard of him. He's a very famous physicist who actually fled Nazi Germany because in the 1930s the Nazis were rising to power, and so Fermi came from Italy, but the Nazis and the fascist Italians were very they hated Jews, and a lot of Jews that could afford it came over to the United States, and this one guy Fermi made this wonderful discovery, and actually a lot of people that went into not everybody, but a lot of people that went into just figuring out how to build the first atomic bomb fled Nazi Germany or fascist Italy. All right. So anyhow, this is what was discovered: is that if you hit a uranium-235, it has to be a uranium-235 atom. So that tells you, the number of neutrons that it has. Of course, all uranium has 92 protons. So if you hit it with a neutron, and this is it just seems trivial here. It's not trivial, okay? What happens is this large atom will break apart, and you'll get 2 atoms. You'll get one of this isotope of kryptonium, which is kryptonium 91, and barium 142. And these are highly radioactive, by the way. But also notice what comes out of that. So into this reaction, right? A neutron, a very energetic neutron, into a uranium-235 atom, and then you have these daughter atoms that come out, but also 3 more neutrons. And then if you have more uranium-235 available, then you could have another splitting going on, and these splittings can happen in very, very rapid succession, and that's called a chain reaction. All right? So, and the energy released in the form of kinetic energy of fissionable fragments that fly apart from one another with some energy, and they eject neutrons, three neutrons in particular, that can go into further reactions. All right, and this is there was a guy, as a matter of fact, that I think the guy that came up with the name chain reaction was another guy that fled Nazi Germany. His name was Leo Szilard, and he actually was living in London, as the story goes. Well, he was living in London. There's no question about that. But he was living in London, and he was thinking about this, and apparently he stopped. He was waiting for to cross the street, as the story goes. Right. So as he's waiting across the street, he realized that, and this is the thing that people classified this almost instantly, that if you hit the uranium-235 and you got to slow the neutron down, and what that does is it increases what's called the cross-sectional area. You don't have to, we're not going to actually do any of this, but anyhow, he realized very quickly you could have this thing called a chain reaction, and Szilard was he was flown to, or I think he might have flown himself from London to New Jersey, right? So he goes to New Jersey, this guy Leo Szilard, and he meets up with a very famous physicist who was Einstein, who also fled Nazi Germany, right, because of his Jewish heritage. He left Nazi Germany, and Szilard explained this vision that he had of this chain reaction, and he got Einstein to write a letter to, I think Roosevelt was still alive at the time, but it ultimately went to Truman, to President Truman, well, I think Roosevelt originally got the letter from Einstein and Szilard, and that's what began the Manhattan Project. They realized that you could build the most devastating bomb that had ever been created on the planet Earth. And of course, that's not the last of the story. There's also nuclear fusion that comes later that we figured out how to make bombs with as well. This is not all about making bombs, but I know it might seem that way at first. The thing is, with the uranium-235, you have to have what's called a critical mass. Otherwise, you get this fissionable material, but it's not going to blow. It's not going to blow up into a bomb, right? And in our modern nuclear plants, nuclear energy plants, we never have enough matter together at the same time to be to make a bomb, right? You don't ever want to do that. The fissionable material is always separated by these control rods, so that the chain reaction doesn't get doesn't, well, it'll never blow. It never blows up. Not like a huge, not like an atomic explosion. But you can have like situations like what happened in Japan. You might have heard of the Fukushima nuclear power plant. That there was a meltdown. So that's called a meltdown, when the fissionable material is not cooled off. The control rods were not in place to cool this thing off, and they had a meltdown, and there's still to this day all sorts of radioactive material in that Fukushima 3 nuclear power plant. All right, so uranium 235 and 238 and uranium 239 are different in the number. They're different